Gases in the atmosphere. Now, in this chapter, we're going to discuss the air, the atmosphere around us, and the gases present in it, and some common reactions or how we can calculate the amount of gases in there, the reactions of those gases, and other relative information. Let's start with the composition of the air. Before we go with the composition of the air, let me explain something that this composition, these percentages by volume are for unpolluted and dry air. So we consider the air is not polluted with any of the pollutants. By pollutant, I mean anything that is harmful for the living things and present as a part of the air or harmful for the planet as well. We also consider the air to be dry, which means we do not include water vapors in the air. When I talk about water vapors, the percentage of water vapors can be different in different areas. This is given in this key point. Air can have anywhere in between 0 to 4% water vapor. And the percentage of carbon dioxide is though small in the air, but is rising steadily because of human activity. So talking about that, nitrogen is present 78.1, 21 for oxygen, 0.9 for argon, and CO2 is 0.04%. So approximately speaking, if we ignore those smaller ones, this is about 4/5 of it, and this is about 1/5 of it. There are many other gases present in very small percentage in the air, specifically noble gases, which means helium, neon, krypton, xenon. They're also present over there. By this, we mean these gases, right? These are the ones I'm talking about. Okay, helium, neon, krypton, and xenon. We have very small percentages of these gases. So that's the composition of air. Now, we do different experiments and different questions regarding the composition of air, though this seems very simple and straightforward, but these fractions are important. Keep them in mind because we're going to consider them. Also, this whole table is to be memorized by the student, right? So moving on, showing that air contains about 1/5 of oxygen. We can do that by removing the air or by relying on this very basic principle that oxygen is a reactive gas and can easily react. Let's go for a practical then. It's pretty easy how we can go for it. For example, practical using copper. What we can do is that we can take two gas syringes, a bigger one and a smaller one, and in between them, we have a silica tube packed with copper fillings. As copper has a red-brown color, that's why it's shown in red-brown, all right? So this is red-brown colored pure copper, okay? So what we do is that we originally start with 100 cubic centimeter of air filled in this one. So you can see the plunger is exactly at 100. And you would see this gas syringe plungers is moved all the way in, so there is no air in this one. So that's what written over here. Let's go through it line by line so we would know the steps of this practical. The plunger on one of the gas syringes is pushed all the way in, this one, and the other one moved out to 100 cubic centimeter. So we know that the apparatus has 100 cubic centimeter of air. Now we're going to prove that out of that air, 1/5 is oxygen. So silica tube is heated strongly using a roaring Pearson flame. That means we take a while to heat it up and then we start with the experiment. The plunger in the left-hand gas syringe is pushed in. This causes the air to pass over over the heated copper, and this pushes out the plunger on the other side. So this is pushed slowly all the way in, and this one goes all the way out. We keep doing in that sequence. We push the left-hand side over to the right-hand side over to the left. This is done in sequence. This is done many times. You can perform the same thing. I mean, pushing this plunger slowly in so that this one goes out, and then push this one in so this one goes out. That's one circle. and you can go for 4 to 5 loops, even more. You may go with 9 to 10 loops. I mean, push this one in and then this one in, this is one loop, and go repeating that a few times. Now the copper reacts. Bunsen burner is moved along the tube so that it is always heating fresh copper that reacts with oxygen. The volume of gas in the syringes falls as the oxygen is consumed. We keep pushing the plungers in and out till there is no change in volume. So roughly after 4 to 5 times, maybe after 10 times, if we are heating it at different points during different times, for example, for the first 3 times, you can heat it in the center. For the next 3 times, you can heat it over here. For the next 3 times, you can heat it over here. So we can make sure that most of the copper reacts with oxygen. We keep doing that until these plungers move slowly to 1/5 of it. And remember, if 100 is divided by 5, that is 20. So approximately the plunger will go from 100 all the way to 80. And when this volume around 80 becomes constant and there is no change, we stop pushing the plungers in and out, right? Let's go with the further calculation. Now, initial volume of air in the system was 100. You will find out the final volume of the air to be anywhere near 80. It can be 79, it can be 78, it can be 80. Somewhere around that. The more accurate you are, the more chances of this number to be exactly around 79. The volume of the air has decreased because the oxygen has reacted with copper in this specific reaction in which it forms copper 2 oxide. And we can work out the data. That initial minus final gives us 21 cubic centimeter, and the percentage would be 21 over 100 multiplied by 100, that is 21%. Out of 100, the number remains the same in fraction as well as in percentage. So the number was 21 as well as the percentage is 21. That's basic mathematics. Make sense?
Can you repeat it?
I mean, when we are working with 100 and we get a number, and then we try to find out the percentage, it would be 21 over 100 as we are working with 100. And in case of percentage, we are supposed to multiply the whole thing with 100, just like that being done over here. So this cancel out this, and the answer is 21 again. So I'm trying to say if we're working with 100, the answer remains the same in percentage. Get the point?
Yes, but why did you subtract 79 from 100?
Because we are supposed to subtract the initial and final volume of air. Let me explain. Air contains, let's go for the first table again, nitrogen 4 over 5 and oxygen 1 over 5. Now, as we used copper, if only oxygen reacts with copper, we will get this kind of reading because only this one reacts. So if we started off with 100 and we subtract the reading we had, which is 79, we'll get this volume. And by this, if 21 over 100 into 100 is equal to 21%. So that means this one is around 21%. And by the way, if 1 divided by 5, the answer is close to 0.2, which means the same thing in percentage. Get the point?
Yes.
If we do not subtract these values, we would never be able to find out how much oxygen reacted. See, we started with 100 cubic centimeter, out of which 79 remained. This 79 is actually nitrogen, which does not react with copper because copper plus nitrogen, no reaction. So that's how we know this 79 cubic centimeter is nitrogen. And the rest of it is oxygen. And that's how we can calculate the percentage of oxygen. Get the point?
Yes.
Good, good. So there are a few things on the sides in terms of key points that we should go with. Wear eye protection and heat carefully to avoid the cracking of glass syringe with the flame, because if the flame touches the glass syringe, it would easily be able to break it. Take care not to push opposite plunger completely out. All right. So after 100, if you're going to keep pressing it this might go out. So don't try to push too hard. Just go with the values and normal pushing. Sometimes students try to press it too much and then the plunger goes out of it and sometimes even break the syringes. So try doing it in a nice and clean way instead of pushing too hard. When doing this experiment, we need to make sure that we use enough copper to react with all the oxygen in the air. So copper must be in excess. There will be some unreacted copper metal at the end. If we do not use enough copper, the value we will get for the percentage of oxygen would be too low because not all of the oxygen has been removed. This is a very important point. Remember, how would we know that some of the copper has reacted and some of it hasn't? Now, this is where the part kicks in. The copper is pink brown and the copper 2 oxide is black. So by the end of the experiment, there should be some pink brown copper left in the system. If all of it is black, you probably the oxygen value you'll get will not be 21% and would be less. If there is some pink brown copper left, you'll get the value 21. You'll get an accurate answer, which ensures that there was excess of copper and some of it reacted and some of it left unreacted. Make sense?
Yes.
Good. Remember the colors. The colors are important as per papers and you're supposed to memorize these colors. So copper is pink brown with red brown and copper 2 is black. Moving on. Remember, we have put inverted commas around air because we're talking about air from which the oxygen has been removed, as most of the air is nitrogen and nitrogen is very unreactive. And so if you put a lighter splint into this air, it would be extinguished. This is the way we can check it. This is a very important point. All right. So if you have just nitrogen left in the air and all of the oxygen has been consumed in this kind of reaction, if you put a lighted splint into this air, I mean, mainly nitrogen gas, it would be extinguished. This has been a part of past papers. Remember, burning requires oxygen. So to keep the splint lighted, we need oxygen. And in this kind of air, if the oxygen has been completely removed, the splint will extinguish instantly, almost instantly. All right. Okay, so if we're clear with this page, can we move on?
Yes.
Great. So there is another way we can put it up. Now, iron needs oxygen and water to rust. We are going to discuss that in a later chapter. So we can use a practical by the rusting of iron to prove that there is some specific amount of oxygen in the air. Again, we're going to prove it as close to 1/5 fraction. Now, iron rusts in damp air, using up oxygen as it does so. We can use this reaction to determine how much oxygen there is in the air. Now, in order to go with this whole practical, we need a conical flask. We need some wet iron fillings. We need a connecting tube. Make sure you airtight this conical flask by using a cork fitted into it. Along with that, this connecting tube is connected to a gas syringe. The gas syringe is put exactly at 100. Or even if we start with some different volume, we can always note it up. That's fine. It doesn't have to be exactly at 100 in the start of the experiment. We may do it with some other reading, but we definitely need to note down the reading. Now, we're going to use the apparatus from this figure. Before we start, we need to know the volume of air present in the apparatus. We can do this by filling up the conical flask in a connecting tube with water and then transferring the water to a measuring cylinder. On the conical flask, we mark the position of the bung and only fill with water to that point. We will assume that a very small volume occupied by iron fillings is negligible. So very small volume compared to the overall one. That's how the iron fillings get wet. So the procedure for this experiment is as follows. Set up the apparatus, put wet iron fillings into the conical flask, and record the initial reading on the gas syringe. leave the apparatus in place for about a week. Remember, this we are saying on purpose. Rusting is a very slow process. It's a slow chemical reaction. So it takes almost about a week for it to rust a little until the reading on the gas syringe stops changing. Record the final reading. We started off with 130. Volume of the air in connecting tube was 12. Initial reading on the gas syringe was 92. And the final reading on the gas syringe was 43. Right? So the total volume of the air inside the apparatus, let's go with that. Conical flask, connecting tube, gas syringe. The total is 234. Okay. Now, the final reading on the gas syringe is 43. The total volume at final reading, again, conical flask. This one is connecting tube, and this one is the gas syringe in the after case. So take it as a before case and take this one as an after case, right? So this value is 234, this value is 185. Subtract them. It's 49 centimeter cube. Now, 49 centimeter cube is the reading after subtraction. We started off with 234 and then multiplied by 100 for a percentage, and the answer to that would be around 21% again. All right. So it's the same way. We're going to subtract. We're going to divide the subtraction value, the answer that we get, by the overall value we started off with, multiply by 100 to get the percentage of oxygen. This is the percentage of oxygen present. Again, it's almost 1/5 of the whole thing. Make sense?
Yes.
Okay. If it does, you would definitely be able to understand the thing we are about to say next. Sometimes when you do this experiment, the answer comes out as less as than 21%. There are some possible reasons for it. The experiment was not left set up for long enough. That's why we said about a week. In some areas where there are drier regions, hotter countries, we might need more than a week, might need 2. So the iron did not have enough chance to react with all the oxygen in the apparatus. The answer could easily be less than 21. The answer could be around 18 or 19, maybe 14 or 15. You never know. Or not enough iron was added at the beginning, so the iron must be in excess. That is, there must be enough iron to react with all the oxygen present. So just like we were saying back in the case of copper, we said the same thing in case of iron. We need ample amount of iron to react with oxygen. And how are you going to get it? Any idea? How would you know that this amount of iron is ample?
Not sure.
Okay, let me help you with that in terms of the moles chapter. Remember, we had the moles chapter to calculate this out. If you have the equation, you can always calculate it. For example, back in practical 1, and I'm not going to scroll a couple of pages, I'm just going to write the equation. I hope you remember in the previous practical, we had this kind of equation for copper. Do you remember that?
Yes.
Okay, so if this was the amount of oxygen and we had roughly 21% of oxygen, we had 21 cubic centimeter of oxygen, we can always calculate the number of moles for it. By that I mean, for 21 cubic centimeter, that is 0.021 divided by 24, and number of moles would be around something 0.07. I don't know. I don't have the calculator in front of me. And right now, do you have the calculator with you?
Yes.
Why don't you go ahead and help me with it? This is decimeter cube, and this one is decimeter cube per mole. So we'll get the answer in moles. So 0.021 divided by 24.
It's 8.75.
8.75.
Times 10 to the power minus 4.
Yeah, that makes sense. 8.75 into 10 raised to the power minus 4. This is the amount of moles. So if these are the moles of oxygen that are going to react, the double amount will react with copper. So it's, as there is 2 with this copper and 1 with this oxygen, so we're going to multiply 2 with 8.75 into 10 raised to the power minus 4 moles. What's the answer to this one? 1.75. No, I think 1.75 into 10 raised to the power minus 3. Am I right?
Yes.
Okay, so if this is the answer for moles of copper, we can simply calculate the mass for it. So 1.75 into 10 raised to the power 3, and the molar mass of, the relative atomic mass of copper is 64 usually. So 64 into this. What's the answer to this one?
0.112.
0.0112?
No,
Without
just
this,
0.
just 112, right?
Yes.
Right. So this is the grams of copper that we require for this one. In order to make sure we have ample amount, take any amount bigger than that. For example, you may go ahead with 0.2 grams of copper, which is far more than this one. Get the point?
Yes.
So with this kind of calculation, we can easily come up with that. Okay. So you may go with 0.2, 0.3, 0.4, anything more than that. If we have 2 to 3 times or 4 times more copper, we will easily be sure that we have excess of copper to react with oxygen. In the similar way, I'm going to clear this up. Can I clear it up? Or do you need a screenshot first?
You can clear it up.
All right. So if we're going to talk about practical 2, by the way, we can't be certain about this equation because usually the formula for rust is different. We usually show it with X's at this level, but let's go and talk about this like this. So what we can do, that's how it's balanced. So what we can do, we can always come up with the amount of oxygen as amount of iron required for this amount of oxygen, right? So as we have taken 49 cubic centimeter of oxygen in this case, so we can always calculate the amount of iron needed in the very similar way we just did for copper. Make sense?
Yes.
And I've used this 49 value over here. Okay, so if you're clear with this one, let's move on. Third practical, we can use phosphorus. Now, phosphorus is a very reactive nonmetal. Now, it reacts with oxygen in the air and it forms a phosphorus oxide. This oxide is very much soluble in water. Actually, it produces an acid upon dissolving in water. Phosphorus does not react with water directly, however, the oxide does. Now, we are supposed to set up the apparatus as shown in figure 13.4 with a piece of phosphorus on the evaporating basin. And then there is a bell jar, and we have a trough that is filled with water, and actually the evaporating basin is floating in water. The initial level of the water is marked on the side of the bell jar with a waterproof pen or a sticker. I mean, like over here or here. Okay. So the bung is removed from the bell jar, this one. So, and the phosphorus is touched with a hot metal wire in order to ignite it. The bung is quickly put back into the bell jar. This must be real quick. If you're quick with this step, your calculations will be accurate or close to accurate. If you're not quick with this step, you're slow, your calculations will change as slow as you are, right? The more slow you are, the more your calculations are going away from being better or precise. The phosphorus burns. The bell jar becomes filled with white smoke, which is phosphorus oxide, and a level of water rises inside the bell jar. The smoke eventually clears as the phosphorus oxide dissolves in water. When the level of water inside the bell jar stops rising, the final level is marked, which in this case you can see can be marked over here and here. So we marked it over here and here. So you can obviously notice there is a difference to the water level rose. So if that makes sense, we can always come up how much the water level has changed. The bell jar is turned upside down, filled with water to each mark in turn, and the water is poured into a large measuring cylinder. It is important that there is still some phosphorus left on the evaporating basin at the end of the experiment, and we have used an excess of phosphorus just like we were using excess of copper or excess of iron, so that there is more than enough to react with all the oxygen. If there was no phosphorus left, then we would probably get a lower value for the percentage of oxygen because not all the oxygen might have been used up. That means a wrong experiment, we might need to redo it with a bigger or more excess amount of phosphorus, right? Now, the teacher demonstrating needs to wear goggles and a face shield to have the room well ventilated. After igniting the phosphorus, the bell jar needs to be held down as pressure rises initially. After all the fumes have gone, the evaporating basin needs to be sunk using blast rod to prevent any unreacting phosphorus reigniting, as phosphorus ignites in a pretty bad way, so we need to be safe about it. All right. That's why we intend for a teacher's demonstration. And at this point, we don't ask from the students to do this experiment. Now, the combustion of elements in oxygen. Some elements burn in oxygen, we call them combustion reaction. Elements burn more brightly and rapidly in pure oxygen than in air because air only contains 21% of oxygen, as we just proved with 3 different practicals. So starting with different reactions, burning magnesium. Magnesium burns in oxygen with an extremely bright white flame. It gives a white powdery ash, and that is magnesium oxide. The white powder formed is not very soluble in water, but a very small amount does dissolve to form an alkaline solution, which is magnesium hydroxide. Clear enough?
Yes.
So we're going to go with different reactions. Make sure that you remember all the visual observations. For example, extremely bright white flame or white ash powder formed, or which is not very soluble in water, stuff like that has to be memorized by the student. Next up is burning sulfur. Sulfur burns in oxygen with a bright blue flame, and this blue flame is pretty good to watch. It's poisonous, colorless sulfur dioxide gas is produced. This is the reaction. This gas easily dissolves in water to form an acidic solution, and the name of acid formed is sulfurous acid, the formula for which is H2SO3. Sulfur dioxide is also known as sulfur 4 oxide. Remember, the 4 is written next to sulfur to show its oxidation state. Make sense?
Yes.
Okay. So sulfurous acid is H2SO3 and sulfuric acid is H2SO4. So these are 2 different acids having 2 different names and 2 different formulae. Make sure you don't confuse them. Moving on, burning hydrogen. Hydrogen burns with a pale blue flame in oxygen, and the product is water. If you ignite a mixture of hydrogen and oxygen, it would explode. This is the big basis of squeaky pop test for hydrogen that we're going to perform in upcoming chapter 18. However, a very little amount of hydrogen is done for this purpose, taken for this purpose, and that little amount of hydrogen gives you a squeaky pop. This is going to be a pretty good experiment for the school lab for the students, because students love this experiment. Every time we come up with an experiment, they would like to go with the squeaky pops. The sound is beautiful, and they tend to perform the experiment over and over again. This comes as a fun experiment in lab. I guess you would be able to do it in your own lab if this routine, Corona routine changes. So remember, we take a very small amount of oxygen for the squeaky pop, and if the amount is a little bit higher, it would explode. So this reaction has to be done with care. I hope the teacher helps you how to get a small amount for a squeaky, enough for a squeaky pop. Moving on, there are some oxides that we need to study. The oxides are actually compounds of different elements with oxygen that can be divided into two categories. Now we're gonna take oxides. These are elements with reacting with oxygen. Let's take E as an element, and we can divide it into two categories. As elements are divided into metals and non-metals. So we can have a metal oxide like this, or maybe a non-metal oxide like this. So we're going to study metal oxides and non-metal oxides separately. These are the two main bifurcations of oxides. Make sense?
Yes.
Okay, let's start off with metal oxides. Metal oxides are actually ionic compounds which contain O2 negative ions. Metal oxides are usually basic oxides, which means they can react with acids to form salts. Metal oxides are usually insoluble in water. Those metal oxides that are soluble in water to form alkaline solution containing hydroxide ions, they actually react with it to form this one. Okay, let's take an example which is probably already written on the next page. No, it isn't. Okay. We might need to write an example over there. Okay, so make sure you do. For example, this is a metal oxide. Now this one is going to react with water in order to form this. See, so we're talking about oxide ion, O negative, O2 negative, being converted into a hydroxide ion, OH negative. So this is not just dissolving in water, it's reacting with water. And that's what this third point explains. Make sure you note down the example because this is going to help you with the revision. When you're done, let me know. Okay?
Okay.
So I'm going to clear it up and we're going to move on to the next page where we have non-metal oxides. The non-metal oxides are covalent compounds. Remember, metal were ionic, non-metals are covalent. Non-metal oxides are acidic oxides, which means they're going to react with either alkalis or bases to form salts. How are they different? Usually these are water soluble and these are insoluble. So actually both of them can react to form salts. Non-metal oxides are often soluble in water, react with it to form acidic solutions that contains hydrogen ions. For example, SO3 can react with water to give us the famous sulfuric acid. Now this can easily give off hydrogen ions, hence acid. Make sense?
Yes.
Let's take an example. For non-metal oxides, we are going to take the example of carbon dioxide. Carbon is a non-metal. Carbon dioxide would be a non-metal oxide. It's a colorless gas. It's most easily made in lab by reaction of dilute hydrochloric acid and calcium carbonate in the form of marble chips. Right? So this reaction produces right here the carbon dioxide we require. And it can also be obtained if metal carbonates are heated strongly. Most carbonates split to give the metal oxide and the carbon dioxide. This is an example of thermal decomposition. Remember, thermal means by heat, decomposition means to break down a component into two or more. Just like here, the example is of copper to carbonate, and we broke it down into copper oxide and carbon dioxide. So metal oxide and carbon dioxide. Another example of calcium carbonate, we converted it into metal oxide and carbon dioxide. So copper to carbonate is a green powder. It gives us a black copper to oxide. As we studied previously, copper to oxide is black in color. It also gives us the colorless gas. But here we see some dense white smoke, as the gas, too much gas is produced in a very little space. Calcium carbonate doesn't decompose unless it is heated at quite high temperatures. This is commercially important reaction because we convert limestone, and this one has the name limestone, into quicklime. So this calcium oxide is quicklime. This is the reaction for copper to carbonate. You should remember the colors of copper to carbonate and copper to oxide. Copper to carbonate is green, copper to oxide is black. Most of the time, the copper compound colors are memorized by the students. So every time we are telling you a copper compound, we are along with that telling you its color, and you're supposed to memorize it. Now, carbon dioxide in global warming, the greenhouse effect, the energy that comes from the sun is re-emitted as IR radiation. Remember that energy that comes from the sun comes as ultraviolet rays. Now, from the surface of the earth, they are re-emitted as infrared radiation. IR stands for infrared. Some infrared is absorbed by molecules like carbon dioxide. The energy is then transferred to other molecules, warming the whole atmosphere. That's what makes Earth a habitable planet. Right? But again, if it heats up the atmosphere a lot, it would become uninhabitable. Because if the environment is too hot for the living things to persist or to survive, it would become uninhabitable. This is what we call global warming, because the entire atmosphere is being heated up due to the greenhouse effect. This entire effect is known as greenhouse effect because the entire Earth is acting like a big, huge greenhouse. Make sense?
Yes.
Do you know what a greenhouse is? Because the greenhouse setups are usually taught as a part of biology. All right, great. Then you would be understanding what I'm trying to say over here. Now, carbon dioxide is produced when fossil fuels such as coal, the solid form, oil, the liquid form, or gas, the gaseous form, are burned. So carbon reacts with oxygen and produces carbon dioxide. Petrol or gasoline is a common mixture of different hydrocarbons. They also react with oxygen in big amounts to produce good amounts of carbon dioxide. It's a hydrocarbon. A hydrocarbon is a molecule containing just carbon and hydrogen. As you can see in this formula, there's only carbon and hydrogen in this formula. We'll discuss them in Unit 4, Organic Chemistry. Well, we are taking the reaction over here to give you a point that carbon dioxide is produced by all of these fossil fuels, be it the solid coal or the liquid oil or the gaseous portion, which we mostly handle in terms of methane. So carbon dioxide is a greenhouse gas. The greenhouse effect occurs when high energy UV visible light from sun passes through the atmosphere and warms up the surface of the earth. The surface of the earth, like any other warm surface, radiates it back in the form of infrared radiation. This IR is absorbed by molecules such as carbon dioxide. When they give out energy in all directions, they heat up the atmosphere. For approximately the last 200 years, the level of carbon dioxide has been increasing. Why? Because we are using more and more fossil fuels. Look around you. We are using fossil fuels for cooking. Fossil fuels keep our homes warm. Fossil fuels to run our cars, run the generators, produce electricity. We're using almost fossil fuels for every single purpose, be it luxury or the daily necessity of life. Right?
Yes.
So this has occurred since the Industrial Revolution, and due to the burning of fossil fuels and most importantly, deforestation, cutting down of trees to create more land for agriculture, Many people believe that the increase in the level of carbon dioxide in the atmosphere may contribute to climate change. The exact nature of climate change is very difficult to know, but some of the things scientists believe could happen are that the polar ice caps would start melting, the ice around Arctic or Antarctic would start melting. In fact, it is already happening. The sea levels are rising because when this ice caps are going to melt, they're going to give more waters to the sea levels, and there could be extreme weathers such as floods, droughts, heat waves, tsunamis, the list goes on. And in this time period, I mean, in starting with from 2000 to 2020 or 2022, we are familiar with quite a lot of tsunamis, floods, droughts, or heat waves. So almost most scientists believe that increase in carbon dioxide will cause devastating climate change, yet there are others who reject it. They claim that the increase in average world temperatures during the 20th century were a part of natural heating and cooling cycles caused by sun and changes to ocean currents. They believe the effect of carbon dioxide is very small compared to this. But whatever the reasons are, we actually have to consider the fact that the entire planet is getting heated up, no matter what the reason. Now, looking ahead, they are going to go with a few parts, but this looking ahead is something that I haven't seen to be a part of past papers. However, what's important and what we should study are these structures. So let's go through those. This is the structure of water. Water is a polar molecule. When I use the word polar, it means it has slight positive and negative charges on it. You would notice that the slight positive charges are shown on top of hydrogen only, while the negative charge is shown on top of oxygen. Now, the oxygen atoms attract the electrons in the covalent bond more than the hydrogen atoms. That's why we have this delta positive and delta negative small charges represented in them. This is not like a complete charge. This is like a smaller charge. The complete charges that are shown on top of electron are simple negative, or proton are simple positive. However, these charges are shown with a delta negative and a delta positive sign, which means it's a little amount of charge and not complete. We also call it pole. That's why we use the word polar molecule. In case of carbon dioxide, in center, you would see a delta positive on carbon, and on the sides, you would notice the delta negative on both the oxygen atoms. The oxygen atoms attract the electrons in the covalent bonds strongly than the carbon atoms do. We say oxygen is more electronegative, something that has the capability to attract the electrons strongly than the others. But the charges cancel due to the shape. A better way of saying this is the dipoles cancel each other effect, because this one tries to pull this away in this direction, this one tries to pull this away in this direction, and they both apply the same force at the same time, just in opposite directions. So carbon has a linear structure, a symmetrical structure, because the forces on the right and the forces on the left are actually canceling one another. Or we can say the forces on both ends cancel each other's effects, which makes carbon dioxide a more vibrating molecule, and it can absorb IR radiation, and then it becomes a greenhouse gas. The entire reason of discussing the structure is to tell you why it is capable of absorbing energy in the Earth's atmosphere, and why not oxygen or nitrogen, or why don't we call other gases as greenhouse gases? So the reason why we call a gas a greenhouse gas is because its structure is built in such a way it's capable of absorbing energy and then radiating this energy into different directions. That's what carbon dioxide can do. Oxygen and nitrogen are both nonpolar. This is the structure of oxygen. I hope you remember from the bonding chapter. This is the structure of nitrogen. Again, I hope you remember it from the bonding chapter. They're nonpolar. They don't have poles because the amount of charge over here and here will not be different, or here, as they are made up of same atoms. They would have equal forces on both ends. This one does not have that kind of structure. There is it's positive in the center and negative on the outside. So the covalent bonds are attracted equally. There are no small charges on oxygen or nitrogen. That's why they are incapable of doing something which carbon dioxide can as a greenhouse gas. Makes sense?
Yes.
Okay. What I've seen in the past 4 or 5 years papers, I don't know about previously than that. I mean, if we start talking about 2016 all the way to 2021, I haven't seen a single question out from this green portion. Yeah, they do discuss carbon dioxide as a greenhouse gas, but just out of this portion, right? So understanding this portion is good. Memorizing all of it, I won't recommend that. And this, I believe, finishes our chapter. Just let me check on the next page, whether we're done with it or not. Yeah, we're done with it. Any questions so far?